Alrighty, so I have A, C, F, and H all depicted here. A is going to be a good diene because notice how it's going to be conjugated here. The rest of the molecule is kind of inconsequential. In fact, it's going to be electron donating, so that's actually going to help its case kinetically. So A is going to be a good diene or a formidable diene. It's going to form a bicyclic compound as a result, since there's already a cyclic substituent here. Okay, for C, a little bit of a different story, seeing as it's not conjugated. It's one whole carbon removed in terms of connection. So there's that sp3 carbon right there that's disrupting. And furthermore, since all these are bicyclic systems, right, they're all constitutional isomers of one another. This one in particular cannot rotate and form that cis diene. So these two dienes, A and F, are actually fixed as cis. So they will actually work just fine, right? They're going to have no problems interacting and forming, again, a bicyclic structure, which we'll get into in a little bit here. And then H is going to be a hard cell as well because there's several bonds or several carbons and bonds in between these two alkene groups. So therefore, this will not work. So C and H will not work. But let's take a look back at B here. So B is also a cis diene that's fixed in its particular alkene arrangement with respect to the ring. So therefore, it is also going to be a good reactive diene in this case. Okay, so let's go over frontier molecular orbital theory, electron withdrawing, electron donating effects, and kinetics. Now, you can really think of the electron withdrawing groups and electron donating groups the same way you sort of memorize them with or aromatic or electrophilic aromatic substitution back in chapters 22/23. Now this is really going to have more of an effect on lowering the energy barrier, where there's going to be overlap or formation of those sigma bonds. So that's really more of the effect. It's not really something you can establish where it's going to be, meta, ortho, whatever. It's a different type of memory bank in your head, if you will. Remember that electron withdrawing groups are going to draw a partial or a positive charge, and then these electron donating groups are going to draw a net partial negative charge from those resonance hybrids. But we'll get into all that in a little bit. And we're going to see how that also affects the kinetics. So if there's a lower energy barrier to overcome and form that particular cyclic structure, the faster things are going to move along, going from left to right. Okay, so let's look at take a look at the molecular orbital diagram of 1,3-butadiene and ethene on figure 24-5 on page 1228. So you can see that's sort of the baseline. There's just hydrogens on both species, and you see a pretty substantial homo-lumo barrier of the diene and the dienophile. Okay, but once you lower that energy barrier, so in other words, if you add electron donating groups to the diene and electron withdrawing groups to the dienophile, that is, let's say if you have an energetic barrier that. For 1,3-butadiene and ethene, it shrinks and gets closer. Okay, so the lower that energy barrier is, the more successful you're going to have these ring formations, or faster, if you will. Faster, more successful, I guess, whatever. Okay, so you can look at that lower energy barrier on figure 24.7 on page 1229, so just on the next page. Okay, so the symmetry about frontier orbitals must result in what kind of interference? Constructive interference, right? Because if you have destructive interference or effectively a nodal plane in between, you're not going to establish any bond overlap or electron overlap, if you will. So constructive. So taking two species and creating one is constructive. All right. So explore the possibilities with LUMO and HOMO of two equivalents of ethene. So you're going to result in destructive interference. Okay. With either possibility. So, that's from asymmetry of phase from the lowest unoccupied molecular orbital. So in other words, they aren't in agreement. Okay, a phase being those plus or minuses that are on those sort of lobes that are figure eight configured. Okay, or figure eight representation, what have you. All right. Electron donating groups will raise the energy of a conjugated diene. So remember that if something is conjugated, that's going to overall lower the particular energy of those pi electrons. Remember that the pi electrons are really what's at play here in terms of establishing bond formation. Okay. Now, conversely, electron withdrawing groups will lower the energy of a dienophile pi star. So, in other words, the lowest unoccupied molecular orbital. Okay, so let's now work with some basis of comparison here. So we're going to compare some dienes and see how that affects the actual kinetics of a particular experiment or reaction, if you will. So look at 24.40 on page 1239. I'll pause this and give you a couple minutes to go over that.